Hi everyone, I'm Tom. Thank you for inviting me. Thank you for coming here and letting me bore you to death or something. So I'm going to be talking about some of my research today that I did at DeepMind, where I work, together with some people from TU Berlin. Concretely, I'm going to talk about a paper we recently wrote called Set Learning for Accurate and Calibrated Models. I should know this better. This is super. Give me just a second to figure out how I can get the same thing on both displays. That would be really nice for me. Yes. Okay. Now we're in business. All right. Third time's a charm. So, set learning for accurate and calibrated models. What that really means is something we're going to discuss very shortly. Like I said, this is work that has been done by Lukas and Robert, who are both at the TU Berlin, Richard and me, who are at Google DeepMind, and Klaus-Robert Miller, who is at both institutions at the same time. So there's nice pictures of all of us. I hope we're still recognizable. I might think my picture is slightly old, but yeah. Anyways, if you see any of the other people walking around Berlin, give them a high five for me and say, Tom said to do this. Let's get started. All right. I don't know if you know what calibration means in general, but to get us there, I'm going to tell you about one thing about neural networks that is not so nice. Like neural networks in general, they're super nice and kind of useful, and they do a lot of things that we didn't think they could do. But sometimes they're a little bit overconfident and wrong about the things that they're doing. So this nice person here behind me, this is Jonathan. Jonathan wrote a really nice blog post where he did a very interesting experiment. He trained a neural network to classify images into either dogs or cats. And then he figured, well, let's see what this network does if I feed it a picture of myself. And you can see the output right behind me on the screen. The network is very confident that Jonathan is actually a dog. Jonathan was not convinced about this. And in fact, he shouldn't be. In fact, I would claim that the network is probably wrong when it says that there's a probability of 98% that this guy is a dog. But it's fairly common that neural networks do stuff like this. And the reason for that is broadly, like, there's a couple of reasons why this is the way it is, but broadly speaking, the main reason is that when we train classifiers, we typically train them to be rewarded for being very confident in their predictions. Like, technically speaking, we train them on to minimize cross-entropy on the training set. And on the training set, we ask it to be very confident, right? To either output 0 or 1, or yes or no, or cat or dog. And typically, you don't have training samples where you say like, hey, how about you say this is half cat, half dog? That just usually doesn't exist in a training set, right? So so you could say this is just overfitting, but I think the main reason here is that the loss functions we typically use, they look at a single example and say the single example is 100% dog or 100% cat, and there's nothing in between. So it's very obvious that neural networks that are trained to always say 0 or 1 will never be able to say, oh, I'm like 5% confident this is true or false, because that's just not what they're trained for. Now, the issue is that sometimes in our life, or in our professional lives at least, we would like neural networks to not be overconfident and actually would like some calibrated score, some better probability estimate of their inputs to give values between 0 and 1. If you think of medical diagnosis, then maybe there's a difference between, oh, there's like a 50% chance you have cancer and you have a 99.999% chance of having cancer. That probably involves very different follow-up procedures and different speeds of follow-up procedures. So my point being, sometimes it's not enough to just have 0 and 1 networks, and sometimes it's not good enough that networks are overconfident, even if they're accurate. Like, the reason for this, as I said, is like, we put an image into our classifier, we do a softmax over it, and typically we ask the neural network to produce an output like this. 100% cat, definitely not a dog, definitely not an elephant, definitely not a car. But that's not necessarily the way it has to be. And but in questions like this, like I said, they come up in a lot of content. So we discussed like applications where you want to have a good calibration, where you don't just need yes or no, but you need a probability estimate. Sometimes you have to handle out-of-distribution inputs, meaning you might have a network that was trained on some data set, but in the real world it now encounters inputs that it's never seen before, like Jonathan and the cat and dog classifier. And while out-of-distribution is like a whole field unto itself, and I'm not going to go into that field for the remainder of this talk, it just helps to know that it makes intuitive sense that it would be nice if we had a neural network that says, well, there's this input, it looks like a human, but I only know cats and dogs, so I'm going to say 0% dog, 0% cat, and just, I don't know, something else maybe, right? So this is something where also overconfidence really hurts us. Another application would be imbalanced data sets. Sometimes you may have a data set that consists of maybe, I don't know, 99 healthy cells and 1 cancerous cell. And then your network would get 99% accuracy if it always outputs healthy cell. Clearly, that's not what we want. That's quite the opposite of what we want. But that's what an overconfident classifier might learn because it's a very attractive local minima. So in those cases, you might want to do something about this. And there's many proposed solutions to handle this, the situation where you want more calibrated outputs. Who of you has heard of Platt scaling or isotonic regression before? A show of hands says 1 out of 100 or so. This is perfect. All right, you're all going to learn something today. Okay, so imagine you have a neural network or some other output of some machine learning tool. And you know that this should resemble probabilities, like the output should be a number between 0 and 1, but it's typically either 0 or either 1 or very close to those two values. Then you can do a couple of things to make this better look like an actual probability distribution. The easiest thing you can do is Platt scaling. Platt scaling literally just fits a sigmoid on top, like a scaling and I think a linear offset or something along those lines. So you fit two numbers and they kind of stretch your probability space a little bit, meaning that if before you had like outputs like 0.001 and 0.99999, then it will shift those numbers together to then be like 20% and 80%, depending on like what you need for this. You could also train an isotonic regression on top of your actual classifier, which is another one of these tools that kind of takes an input distribution and outputs something that looks more like the actual distribution. If you ever do scikit-learn, then like isotonic regression is like the first tool you try because it's just there and works fairly well. The problem is you'll need a separate training set to fit your Platt scale or your isotonic regression. So it's not ideal. Another way you could do is label smoothing. Label smoothing is this idea that instead of having labels that are zeros and ones, you have labels that are, I don't know, 10% and 90%, so 0.1 or 0.9. So you just add some noise to your labels. This is nice because suddenly your sigmoids aren't forced to the extreme values anymore, so you have more gradient flows, training goes a little bit easier. The network tends to be less overconfident, but it still feels kind of weird because you're adding noise indiscriminately to your training set, and that's not really what you want. And while label smoothing is nice, it's not perfect either. You could do class weighting. So in my example before, like 99 healthy cells, 1 cancerous cell, you would probably want to adjust your loss function to say, hey, whenever there's a cancerous cell, then any misclassification should count 100 times more than if you have a healthy cell, just because you have 100 times more healthy cells than other cells. So those are kind of very easy tricks that you kind of learn sometime at university or while you do in your practice. And they're nice, but they're not always ideal. So a couple of months ago, we decided to try and do something a little bit different about this. And that's the method that I want to be talking about today. So we had this new idea. Really cool, really exciting. No one thought of this before, promise. Instead of having a single image that you feed into a neural network, we're going to feed it several images combined so that the network can learn to kind of not just look at individual images, but kind of contrast images with one another and kind of have an exchange of information, if you will, in the gradients of your network. The idea is based on some fairly common experiments in cognitive science. We'll show later that this achieves better calibration and uncertainty estimates. And the cool thing is that this also does fairly well in settings where you have like limited training data or heavy-tailed distributions. All right. Okay, so question to the audience. I give you 3 images. Which one is not like the others? Who thinks it's image number 1? Interesting. Who thinks it's image number 2? And who thinks it's image number 3? I've seen at least one person vote twice, so this is weird, but all right. Yes, I would agree the elephant is kind of the elephant in the room in this case. It's the odd one out. If you do cognitive science, psychology, you might know experiments like this as like odd one out experiments, or in this specific case, it's a 3 alternative forced choice test. And you use tests like this to kind of get a sense of how humans perceive their world. Like in this case, or I thought it was kind of obvious, but the audience does not agree with me. But typically this gives you some insight into how we perceive things. Like if the middle image wouldn't be a cat but a dog, then it might have been a completely different result if I asked here in the room, right? Because then some people say, oh, but dogs and elephants, they're kind of the same color, and this, I don't know, or they're both not wearing glasses, or I don't know. Point being, this gives us some information of the world, and it gives us some information about how people contrast images with one another. And this kind of gave us the idea, hey, can't we try the same thing with neural networks as well? And the way we did this, it kind of looked like this. We call this odd K out learning. It's similar to this odd one out task. And spoiler alert, the K in our paper will always be 1, so I would call it odd one out from time to time. But the idea is this. You show the network several different images. Some of them are of the same class, and there's a couple of odd images out that are like outliers. Like in the previous example, this would be an image where you have like 2 cats and 1 other class. And then you ask the network to identify the majority class, right? So you feed in a set of 3 images, and the task is to predict the class that it sees most often in that set. So if any of you do image classification, it's the same set as like Cypher or ImageNet or something like this. Same task, except that now you don't have 1 input, you have 3 input images. Right? So the implementation is fairly similar, fairly simple. You take a vanilla network, it can be a ResNet or a vision transformer or whatever. And for each image, you extract a representation. This is typically the last hidden layer representation or something. And then you combine the 3 representations that you have. In our paper, we did something very silly. We just added them all together. We tried different things, but adding them all together kind of works best for us. Right, so you take, we can discuss about notation. I would have closed my parentheses here, but anyway, this goes too far. The idea is really, you have 3 representations, you combine it into 1 representation, and then you feed that 1 representation to a final layer that does the classification. And that kind of asks that last layer to predict the majority label, or the label of the cat in this case. Are you with me so far? I should have said this at the beginning. If something is unclear to you, it might be unclear to you to someone sitting over there or over there as well. So please ask questions at any time where you feel like I've lost you. Now would be a good... Yes, go for it.
Calibration. Sorry, I think I didn't understand. But is calibration just predicting maximum entropy when we are out of distribution?
Yes. No. What it means is that imagine you have a neural network and you feed it an image and it says, oh, the probability of this being a cat is 80%. Then you would expect that in 80% of the cases where it says 80%, it should be a cat. Does that make sense? It's a little bit weird to say it like this. I'll write it down, maybe that makes it clearer. Say, I don't know, you have the probability of like your label being 1, given you have some input, right? And what you would like to have is that when you learn this probability, it's the same probability distribution that you also have in the real world. But typically what a neural network learns, like if this is the P of the neural network, then it has a huge spike here and a huge spike here and nothing in here.
Due to the one-hot encoding rather than the cross-entropy?
It's due to both. I mean, yes, if you could find input images or input samples where you can say like, oh, the probability of this is like 80% instead of 1 or 0, then I would agree. But the reality is that actually an image either contains a dog or it doesn't contain a dog. So it's very hard to find an image that contains 80%, like this 80% probability of containing a dog. Right.
Jason was the person that we... What would be the expected calibration there? Would it be 50% dog and 50% cat? Because this would be nice.
Good question. I mean, my feeling is that if you ask someone on the street what the machine should do, if you feed it, it should say 0% dog and 0% cat. But speaking as a machine learner, that's really hard to achieve. And there's probably some other solutions that we need to find to deal with this problem. That's why I said auto distribution is a super tricky topic, and it's something that I would like to exclude for this talk just because it's super difficult. With that said, that's a super hard problem just because a lot of people have stumbled over this before, and it's a problem that, like, if you want to do research on this topic, you're probably in good company because this is a problem that a lot of people have and a lot of people would like a solution for. Yes, did I confuse you more, or was this helpful? All right, okay, cool. 2 more questions. I have no idea who was first, so I'm going with left first.
Of an image that is 8% a cat.
I probably cannot, but my point is this. Actually, do you mind if I'll have some slides explaining this point later on. I should have put them first, but I didn't. I'll come back to this later if you don't mind. Yes.
So if I understand correctly, the neural network's already trained on a normal cassette.
Yes.
Mm-hmm. So as I see it, then why wouldn't you take the average of the embeddings?
Mm-hmm.
You would more or less have the cat prototype centroid if you add a lot of cat representations. And then you have like this random perturbation.
Mm-hmm.
So why aren't you using the average waves?
I mean, the difference between adding and averaging is it just that I'm not dividing by the number of images that I put in, right? So like the vector points in the same direction, it just will be longer if I don't divide. To be honest, I don't quite remember. I need to check the paper. We might have put a layer norm after this layer anyways, and then the length of the thing doesn't matter anyways. But mostly what we do is we combine all of these. We could average as well. We sum or average. And then we train another layer on top. And for this other layer on top, it doesn't really matter if the vector is longer or not so long. I mean, it matters a little bit for optimization and like learning dynamics, but it doesn't really matter in terms of expressiveness of the model. Yes, but that's the same, like, it's the same issue that with dropout, right? When you do dropout, you also divide by the dropout probability, so the vector doesn't get too large. Only that in this case, oh no, well, I take that back. We should have probably taken the average now that I think of it, for a point I'll make later, but yeah, it's a very valid point. But my point would be that it mostly doesn't matter. I would, now that you mention it, assume it makes a little bit of a difference when we do inference. Yes, it does a little bit of a difference there. But yeah, in general, it shouldn't matter too much for learning. Yes, other questions? Yes.
Is the K here a hyperparameter?
Yes, K is like how many odd points you have here. It turns out that it doesn't really matter what K you pick. So we always set it to 1 just because that's computationally less expensive. All right, cool. I'll go on, but keep the questions going. This is, yes, amazing. Go for it.
So first, for the context of this, is it the case that you've already done the standard supervised training on?
No, you would train this from scratch. Yes.
And also, what if you're comparing adding the features to, like, why would you do the summation or?
Because it's easier to then, so I'll get to this in 2 slides, but in general, because if I do concatenation, then at inference time where I only feed one image through the network, what do I do then? Do I just pad zeros? I mean, I could try that, that's true. But if I just sum them up, then I don't need to change my network at inference time. But otherwise I would have, if I just want to feed in one image now, I would feed that one image and 2 empty images. Just because my classification layer on top of this whole summation would now expect like 3 concatenated images. But we could, we might have even tried concatenation, to be honest. I don't recall. No, I think pretty sure we did summation exclusively. Yes, but valid question. Alrighty. Okay, so that's kind of the idea in one more slide. With odd k out, we just do this kind of thing where I have like, well, this is the majority class, so this is what we kind of want to get out of the network. And what the network will produce in the end is really something where it says like, this is most likely a cat. It could be an elephant. There's a slight hint of dog in there, but it's definitely no cars. Whereas in the standard training, you just say cat, nothing else, just cat, 100%. So this is kind of what you train the network to do. And one of the nice properties of this whole thing is that since you always give it a different class as well, the neural network can never say, oh, this is 100% a cat, because there's 1/3 of an elephant in there anyways. And there's no way to get rid of that. So you force the network to kind of never be super 100% sure about one single class. Yes. My last function is still cross-entropy, but cross-entropy where I'm trying to predict. We tried 2 versions. Sorry, there's again the echo. It's totally not my fault. We tried 2 versions. You could either say, well, when you have these 3 inputs, then the label is cat, or you could say when you have these 3 inputs, the label is 2/3 cat, 1/3 elephant. Either works, but since it doesn't make too much difference in practice, we used one-hot encoding for most of our experiments. Yep.
Try it, and I don't know, maybe use this but just use the logits, so not use softmax at all, but just use the logits and then cross-entropy correctly on the logits.
Why would you expect that to work? I mean,
but it makes sense in some cases. Use cross-entropy on logits directly.
Yes, but you kind of lose a little bit, like you lose brownie points with the theorists because they would expect that cross-entropy always is on valid probability distributions, and with logits you don't have numbers between 0 and 1s. We haven't tried it. Yeah, I don't know. All right, so that's on training time, and then when you do inference, you can still just feed a single image. You get rid of this summation because the summation doesn't matter here, and that's why I think it was him anyways who said, well, if you do average, it kind of is nicer here because then kind of this input and this input are roughly on the same size. And that's a totally valid point that I didn't see when we wrote the paper. But the point being, like when you do inference, you pay no additional cost for this. Like this is totally free, which is nice. But you would still expect that the probability distributions you get out for this in the end are not just one-hots, but they're actually meaningful distributions. All right.
Do you always require that there is a certain number or like the same number of data points per forward pass, or can like the same number of images per forward pass, or can it vary?
We haven't tried varying it. In theory, you could. Right, this goes back to the point of the other person that when you do concatenation, you couldn't easily modify this, but since we do averaging, we could do this, but we never tried varying it. Okay, nice. So that is k out in a nutshell. And now let's look at how this performs in practice. We tried this on a bunch of smaller data sets. What you see in the x-axis here is the number of training data points we trained this with, because we expect this method to be most useful when there's a small amount of data points available. And we tried this in two settings. We tried this once when you have like uniform distribution over classes, which is like the standard setting. And we tried it with a heavy-tailed class distribution where like 70 to 90% of the samples are of the same class. Our intuition being that this method might also help a lot for like heavy-tailed or imbalanced data sets. So we wanted to try this. We compared to a bunch of like fairly standard methods. So OKO is like the method I just presented to you. Vanilla is just cross-entropy. Vanilla plus label smoothing is label smoothing. Weighted cross-entropy is like where you weigh according to the class distribution. So this should, for the uniform distribution, should pretty much match the vanilla line. Focal loss is like a state-of-the-art method. It involves reading a whole paper, so I can't really explain it in 2 sentences. But that's kind of, if you want a more involved method, then focal loss would be your go-to, or one of the go-tos. Batch balancing is just this idea of with each batch that you train with, you make sure to sample the same amount of samples from each class, and you can combine batch balancing with label smoothing. Those two are not really published methods. They're just things that we thought of that would be interesting alternatives as well. The takeaways from all of these nice graphs is that, first of all, with small amount of numbers, OKO does fairly good. Once you get to more data points, like after 10,000, say for here, kind of the methods merge together. So you don't see a lot of difference for large data sets. And the other nice message is that for heavy-tailed distribution, this also works really nicely. We do have some follow-up work on like specifically medical applications, where we also see a lot of benefit from doing OKO. But this was kind of promising, because when we set out to do this work, we imagined a method that would be good at calibration, and in the end it turns out to be good at accuracy as well, or not worse than not doing it. Yes, there's a question.
So now the distribution is not so focused on one class. How did you test that the other class that has a higher distribution of 2 is actually a bit similar to that picture? So if there's a, I don't know, there's a picture of a cat in the foreground, and then would it predict the dog, or is it random? Like, would the probability for dog be higher, or check that?
Interesting question. We didn't test it, but it would be a nice test. My guess is that the bigger object would win out, or it might even output 50-50, but I really don't know.
But isn't that like a validation to the mean, right? Isn't that?
It should have. We should have thought of this. We didn't. That's on me, I guess. Yes.
Data sets, some of those are like pretty simple data sets, a bit like.
Mhm.
Have you about one of something?
We did try ImageNet as well. It turns out ImageNet is a little bit more tricky computationally when you feed in 3 images all the time, but still doable, and their results are kind of same as vanilla, just because the data set is large. So it's like there you don't really see an advantage in accuracy for OKO. Yes.
I missed this, but is there like a compute?
No, there isn't. But in Essen, oh wait, is there? I don't recall there being one. But to be honest, it's been some time since we wrote the paper, so I might have forgotten. But I don't think so. In general, yeah, it's just 3 times more expensive in training and same time for inference. Like that would be the case if it converges at the same speed, but to be honest, I forgot about the speed of convergence. Yep.
Can you maybe put the intuition of the method in like a couple short sentences? Because for me, it seems like it's more just the regularization technique rather than actually focusing on this probability
Mhm.
pronunciation.
I mean, it can be a little bit of both. I agree that there's definitely some regularization happening because of this, and that might be the main effect. For me, the intuition, or there's 5 authors, and we kind of have 5 different intuitions for why this works. I can only give you mine. My intuition is, and I'll let you decide if this is regularization or not, but my intuition is that if you feed in 3 images and there are 2 different classes, that means that for each sample that you feed in, you kind of get 2 directions that the network is going to train to, right? Because you get 1 signal for elephant and you get 1 signal for cat, which means that the neural network will have to learn A, the commonalities between those 2 cases, like, and has an easier time learning them, and B, the things that make them different. And the other thing it does is that whenever you feed, the other thing it does is that you can never, or it will be very unlikely that your network will output 100% cat or something, just because there will always be this elephant there as well, and it can't ignore this elephant because some other time it might have seen 2 elephants and 1 cat. So there's elephant detectors in there, and they will fire. And that means that the network will have to say, oh, there's an elephant here as well, even though there's a very strong signal for cat. The gradients in the network flow in such a way that it can never just then turn those off and just say, okay, well, if cat is stronger, then it overrules all of the elephant neurons that I have. Yes. Wait, sorry. You were first. So someone in this region. Okay.
Right before I handle this question, so if we say in the resulting network, so the resulting network will never predict something with 100% confidence and 100% probability, could you?
I mean, during training, during inference, I'm not sure. During inference, it might still happen.
Could you like, say, hint or like move the network towards being more confident on those examples where it's actually kind of more linear, or it should be more clear which class it belongs to? Like, for example, doing training, like mixing or two, like having part of the training or having some samples with this OKO with several samples and some samples with samples only from 1 class, only with a single sample.
Cool. That would be something we could try, but we never tried it. Yep.
At least what my intuition now, I'm not so involved, but let's say you sum up all the cats, that would mean all the kind of very unique features of cats get blurred, right? They get kind of normalized.
Mm-hmm.
And then you have a random perturbation. So I think, for one, you start by that becoming probability of very specific.
Mm-hmm. Right. Mm-hmm. Interesting. Yeah, that's an interesting way of thinking about this. I could imagine that. So your intuition is that you have 2 cats, so those cats merge together, right? Because there's only the point is to predict the cat. But maybe instead what happens is that the network develops unique features for each of those 2, and they just both fire, because the same cat, like the cats that have been seen together in that 1 sample might also occur in different samples when they're not together. And so it means that, okay, if those 2 cats come together, then let's say this neuron, and this neuron fires, and they kind of then get the signal that, oh, we should all be active whenever there's a cat. But then there might be another sample where there's this cat, but some other cat, and then suddenly this neuron doesn't fire again. And then this doesn't increase now, but there's these other cat detectors that do increase. So I think it's still possible for all the neurons to specialize. But again, this is something that we would need to look at. But it's an interesting intuition, and it could very well be that you're right.
Because I think, like, the biggest problem with these, like, focus on 1 class and very Isn't that's the gradient of the soft mix, right? You're trying to just play in this little kind of area that has a very large gradient. You're trying to shift forward. That's super volatile. Wouldn't it make more sensible to just try a different loss function?
I mean, it would definitely be interesting to try a different loss function, but then you would be writing a whole different paper. In the sense that, like, you're welcome to try. We think, like, I think this method works well as it does, which is interesting, but definitely there's still a lot of room for improvement. If you can come up with a different loss function, that would be nice, and I would love to read that paper.
Since it's a strong gradient, sorry to interrupt. We will have.
Okay, yeah, right. Sorry, I'm over time. I realize now. This is not my fault. It is my fault. Sorry. All right. Okay, this is on me for allowing questions, but let's continue this afterwards. All right. Okay, cool. What about calibration? I promised I'll explain a little, that I would explain a little bit more about calibration, and these are the little slides I prepared for that. All right. Okay, how to evaluate calibration. Let's imagine for a second that you have some samples, right? You have, in this case, 10 inputs, and the outputs you get from your network are these up here. I didn't put it here, but let's say some of these inputs are labeled with zeros, others are labeled with ones, and we don't know which are which for now. We just know that, okay, given input x0, the network outputs probability 0.9, x1 20%, and so on and so forth. Okay, well, now to kind of get a feel for what calibration is, we'll do the following. We'll group the inputs together based on, like, if the output of the network is like lowest third of the probability space, middle, or if there's a high probability of these inputs being predicted as class 1. So I get 3 sets out of this, right? These are the inputs that have fairly low probability according to the network to be class 0, middle probability, high probability. What you do then is you kind of average the predicted probabilities, and it turns out that, well, in set 1, the average probability is like 15% or 17%. In the middle set, it's 45%, and here it's 82%. That's all well and good. Now, the interesting thing is to look at what the actual labels of these data sets are, right? So let's do that for a second. Let's pretend the real labels were like these, were like, actually, of these 3 points, one was actually a true data point. So it means that actually the relative frequency of positive examples should be 33%. And here it's like half of the points, so like 50% are actually class 1, whereas the network predicted that 45% of them are class 1, and here it's 80% instead of 82. Whoops. So now what we can do is we can kind of draw this on a line. Sorry, I kind of forgot to include that slide. Now I can do this on a line, right? Where we have like, this is like the confidence that we get from the network. And the confidence we got is, let's say, at confidence 0. Oh, I'm really bad at writing, sorry. At 33%, the network actually gave, said it was 17. And at 50%, the network said it was 45. And at 80%, okay. Then let me finish quickly. At 80%, it was actually 82%. Right, so we can kind of draw this line, or for reasons that I'm a really bad drawer, this is actually a straight line, but it shouldn't be. So we come to a line like this, whereas actually a well-calibrated network would have a 45 diagonal, meaning that if the network predicts that, well, 50% of the images should be class 1, and when we run this test a couple of times, we should actually run up to like 50% as well. And this should hold true for every output. That's kind of the usual measure for calibration. And we can we can do this experiment for like when we bin probability distributions, and then we get results like this one. Like, okay, the network says like 20% of the so when the network outputs probability distributions between, let's say, 0 and 20%, then actually roughly 20% of the times it should include a real example. But usually if you just train vanilla cross-entropy, it's typically 0%. Whereas it's very overconfident here. And the different methods all have different behaviors for this. And the ideal, like an ideal curve should look like this one, like the focal loss curve, or like the O loss curve. And this is the same for like different data sets. Like there's a bunch of more of these plots in the paper, but that's the gist of it. This is how you kind of learn, or how you kind of evaluate calibration performance. You can turn these graphs into numbers by computing something called the ECE, or the expected calibration error. But if you want a graphical representation, then this is kind of how you evaluate how good your model is at predicting how often it is right or wrong. Yes. Okay. So intuition of why OKO works. I kind of talked about this before. So like each input set contains information about two different classes, and then the task that you have now is to kind of give, this kind of gives you contrasting or ambiguous information that the network needs to learn and deal with. One very easy way to think about this is that it's kind of a guided label smoothing. So now instead of saying, oh, I'm just uniformly adding some noise to my labels and make all the zeros into 10% and all the 100% into 90%, you have a more guided thing where now you make suddenly this 2/3 cat and 1/3 elephant. So it's still a label smoothing effect, and we know label smoothing is kind of a regularization, so your point is totally valid. This is kind of a regularization as well. But it's a little bit smarter way of doing this than just label smoothing, which is just without looking at the inputs, adding noise to all the labels. Yes. Okay. Yeah. Summary. So this is a fairly simple trick to improve neural networks. The basic idea is to use sets of different images. It improves calibration. It's equal or better in accuracy as far as we can tell. It can be used with any network architecture, which is really nice. It has some nice theoretical properties that I completely skipped over. Yeah, if you want to read the paper, it's online. We have some small source code even there if you want to look at how this could be implemented. Yes, and if you didn't have questions before, then maybe now you can think of some. Sorry for being over time, but maybe I'm still allowed some questions. All right.
Okay, thank you for this absolutely fascinating talk. I find it amazing that it's such a simple and elegant idea, yet nobody seemed to think about it up until now. So I would say that now we do 15 minutes of questions. I'll be very strict with the time. And yeah, go ahead.
Right. I don't know.
Wait for the mic.
Oh, sorry, I should have picked someone there then. Ah, damn.
Thank you for the talk. So when you want to mix the representations of different images, you have in the example just summation, or I guess average is the same. Do you try other ways to do it?
Yes, we tried doing a transformer first, but that kind of loses this whole simple idea of then at inference time having to do nothing, like to not modify the network at all. Because at training time, you would need this whole transformer, and at inference time, you suddenly need a transformer that just has one input, and that's kind of weird. So that's something I remember us trying. There might be more in the appendix of the paper that I'm now not recalling, but there are probably smarter ways of doing it. For example, doing average pooling or averaging instead of summation. But
and maybe how could you expand this to use it for segmentation, where you need like fine details of the image and not just an overall category on the image? Like, for example, if you want to pick the one with the glasses and not the fact that it's an elephant, how would you do that, for example?
I mean, if you just want to pick out the glasses, then you would have to, wait, maybe I'm misunderstanding you. You don't want to say that the glass is the odd one out, but you want to pick out the glasses out of the whole image.
Yeah, something like that.
I mean, in general, this is an approach for classification. I'm not even sure what calibration means for segmentation. This would probably be a longer discussion because we need to think about what we actually want to achieve in that case.
Yeah.
Sorry, I have no idea what the thing is. Yes.
Hi. Is the interest in the medical application or the continuance of the paper because you have a limited amount of samples that are fairly well classified, and given the curves you showed before, there might be a fairly severe upside to using a model like or an approach like you described here?
Yes. So our intuition is that this would work well for medical data because there you often have class imbalances, and you often have heavy tail distributions as well. So that's our main motivation for trying it there.
Can you describe a little bit the process of going from the initial idea to the paper in the end? Like, what was the origin of the idea to begin with? And also, what was the timeline? Like, how long did that take? And also, like, for example, along the way, were there moments when you thought, this isn't going to work, and then you tried something slightly different and it worked much better, this kind of thing?
Okay, the timeline for this was fairly long in the sense that Lucas, the first author, and me talked a long time ago, and then I had a child and was kind of spaced out for a year, and then I came back and then I talked to Lucas again, and then we kind of came to this, but there was probably a lot of thinking that Lucas did in that 1 year where I was spaced out and playing with my child. Then when we actually had the idea to like get it all set up, implemented and all, took definitely less than a year, but I would need to check my emails to tell you exactly what it was. In terms of dead ends and how he got to this idea, Lucas has a background in cognitive science, and he was very fascinated by odd one outs and 3 alternative forced choice tasks. He'll be here giving a talk at the event as well, and we'll talk about other ways of doing cool stuff with odd one out datasets and odd one out tasks. And this was just one variation that we eventually tried. There was Klaus Robert Müller involved, who was kind of pushing us to find a way to use something that we can use for unbalanced datasets, and it eventually all came together. I can't really tell you how, but just I remember there was a whiteboard involved that people kept writing stuff until something stuck. Something along those lines.
Thank you.
What size for the input sets is used by your final model?
Say that again.
What size for the input sets? You mentioned K being just 1, but what's the size of the set?
So K is 1. Like we tried different things. Like we tried also different Ks, different like size of majority class. But those kind of things didn't matter too much. And for number of training points, it's, as you can see here on the x-axis. Oh yes, that brings you back to motivation for this. One motivation for this was that initially we had this weird idea that imagine you only have 10 samples per class. So you have a super small data set. But if you build triplets, like you can build a ton of triplets out of 10 sets per class, right? So we figured, this should work well for small data sets, because now we suddenly have an exponentially larger set of training samples available to us. Which I'm still not sure is a good idea, because like there's not more information in the training set, you're just using it differently. But anyway, that's kind of how one motivating factor behind the idea as well. That doesn't answer your question. We mostly tried this with smaller data sets, like with small number of training data points.
I'm sorry for bringing you back to this, but what's the performance on out of distribution?
We didn't use this on out of distribution.
You didn't try at all?
Not that I know. Like maybe one of my co-authors tried and didn't tell me, but we didn't try this on out of distribution. Like I said, I'm struggling. Like I'm not an expert in out of distribution, but as far as I can tell, that will require different tricks to work as well. Because as someone mentioned in the beginning, like if you only have two output nodes and neither of them should be active, then kind of like, does that work? How does that work? It definitely doesn't work with cross-entropy, I think. I don't know.
What is like an optimal value for K? Did you try out different values? Or are there diminishing returns with the increase of batch size?
We tried different values and we didn't see much difference in performance. So we stuck with K equals 1. Yeah, we tried 2, 3, we tried different.
Did you use what batch size did you use? Like, did you play around with that? Like, how many? You have one odd one out, right? And then you have all the other in. So that's like kind of how many samples you kind of use for the.
I would need to open up the paper because I have a table in the appendix somewhere. Does this work? I mean, let's see. No, there we go.
Because the signal of the odd one out should decrease, right? If we have more samples.
That kind of should happen, but. Did I mention that I skipped over a lot of math in this talk? Okay, so here we have different case. And you can kind of see like the numbers don't, most of the time they don't differ too much. So we stuck with K equals 1, but we could try different things. But yeah, and I thought we also had experiments where we had like the majority class more samples, but apparently we haven't put those into the papers. I couldn't tell you. Our takeaway was that it doesn't really matter, so we'll stick with K equals 1 because that's computationally efficient. All right, there were probably more questions.
Thanks for the talk. I all the time had to think about like data augmentation. Like you have this mix up all kind of different kinds of doing this augmentation.
I was afraid someone would ask about mix up.
No, I don't care about the specific type of augmentation, but you do it at a different step, right? You don't do it at the input level, you do it on the representation level. So do you think that this is the big difference? And the type of augmentation that you do probably does not matter so much. So
it's a good question. So for one, evaluating against mix-up would have been interesting. For those who don't know, mix-up is this idea that you kind of smash two input images together and then feed the resulting output image into the classifier. That's kind of similar in the idea, right? Only that they have two images, we have three. I'm not a big fan of mix-up just because it feeds images into the network that are not existing in practice, right? It's this overlay of two images and that's kind of weird. And though it does seem to help, I don't like it because it feeds these weird Frankenstein images into the network. With that said, it works well. We should have explored and we might still have to explore when mix-up works better and when this works better, what the trade-offs are. I don't really know I don't know if they lead to different representations, which is, I guess, is what you're asking. Is like, kind of, do they learn the same things or different things?
Yeah, the thing is that the augmentation that you're doing is happening after the embedding step, right? And I'm just wondering if this is the big difference, that you do the augmentation later, the later step, and the type of augmentation is not so important. It's just really in question.
Yeah, it's hard to say, but like the objective is also different because in mix-up you really have like these soft labels between two images, whereas here you predict the majority. So in mix-up it's never, or in mix-up you could have images that are strongly cat or strongly dog or like 50-50, whereas with us there's always this setting of like 2 versus 1 or 2 versus K.
All right, fair enough. Thanks a lot for the answer.
Okay,
okay. Sorry.
We have about 3 minutes left, so let's maybe go for 1 or 2 very quick questions from the right half of the group.
I'll still be here. We can ask questions, like we can talk afterwards as well if that is helpful.
Very nice, yeah.
Thank you. I have 2 very quick questions. One is, what's the impact on training time?
So this was asked before. It depends a little bit. Like obviously, like one sample takes 3 times as long because you need to feed through the image. But then the question would arise: does it converge earlier now, or does it take longer to converge? And I know we ran those experiments, but I forgot. So maybe they're in the paper. If they're not in the paper and you're really interested, send me an email and I will dig up the experiments.
All right. And the second question is, are you planning to release some implementation for this, or did you already do that?
So like the implementation of OKO itself is like half a line of code somewhere. Half a site, sorry, not half a line is a little bit too much. Like, it's not super long, right? This is the whole, like this is the head you put, an index you would put on top of the network. And all it really does is say, oh, if you're in training, then just sum the different x's up. It's fairly easy to implement. As for like the whole experiments that we all did, I don't think so. Not because we were evil, just because it's a lot of paperwork to publish source code at Google.
Makes sense. Thanks.
Okay. Maybe the last question over here.
So I have 2 questions, but let me only ask one.
Make 2 questions with an end in there, then the guy can
So I think in a practical application, I would be interested in the case, like for example, for medical images, where you only have a view. Have you tried, or do you have an intuition of how well you could fine-tune a pre-trained model like a ResNet with your kind of training procedure, and would that also help? Or do you have to train it from scratch?
I mean, the question itself is not, you don't have this only in the medical domain, right? It would be a fair question to ask here as well, could you use a pre-trained model? The answer is we haven't tried, so we don't know. Specifically for medical applications, some of my co-authors are working on specifically that, and you will probably have to ask them to share the details, because that's not like, it would be mean of me to tell their work for them. That's something that's their prerogative, not mine. Lucas is one of those people, so if Lucas comes here in a couple of weeks, ask Lucas about this.
Okay, thank you.
Awesome. Then this would be the end of our open discussion. Feel free to ask Tom any of your questions right now, after a big final round of applause.